give an overview of the approaches to prove lower bound rather than complete statements of lower bound. And then I'll tell you about the depth reduction by Brilliant et al. That I was mentioning in the morning. I'll try to give the full proof of the theorem there, and I'll present a full proof of monotone circuit lower bound. The monotone circuit lower bounds in Boolean setting were originally obtained by Rasborough. In the arithmetic setting, the proof is much easier, and it's due to Gresham and Smith. And for the depth reduction part, thanks to Ram Prasad for helping me solve it, right? So, really this should have been approaches to using lower bound. I'll just tell you very quickly about these 4 approaches that have been investigated in the recent years towards using lower bound. One is what is called geometric complexity theory, has been pursued by Kayal and Monotone, and via the real tau conjecture. Recently it was pursued by Pascal Coiran. It has connections to q-nomial theory. Via de-randomization of identity testing, we will see more talk on identity testing. And as Amir also said in his talk, we should try to prove very strong lower bound for low depth circuits and thereby obtain lower bound for arbitrary circuits. So I'll just quickly tell you what all these are trying to do. So let me start with geometric complexity theory. So it deals with the symmetries of a polynomial. So what are the symmetries of a polynomial? It's all linear transformations which keep a polynomial invariant. So formally, it's suppose if you have a polynomial f on n variables, the degree for now is not important. Then the symmetries of the polynomial are all invertible n cross n matrices A, such that if you make the linear transformation corresponding to A and apply that to F, it remains invariant. So maybe a simpler example might be better. For example, consider just one monomial, say x1 through xn. Now, what are the symmetries? First of all, you can permute all the variables. So that doesn't change the product. But you could do something more. You can multiply a variable by say 2 and another variable by half, and the product remains the same. And it turns out that if you have a monomial product of distinct variables, these are all the symmetries of that polynomial. Okay. So now, let's say a polynomial f has this property called characterization by symmetries if the following holds true, that essentially the group of symmetries of the polynomial completely determines the polynomial. So formally, if for any other polynomial of degree d, if the symmetry group of G is the same as F, then G must equal F. If that holds true, then we say F is characterized up to symmetry. So now there's a remarkable theorem that says that both the determinant and the permanent are completely characterized by their symmetry. So one way for you to describe these polynomials to me, the determinant and the permanent, is not to tell me what are the monomials and what are the coefficients. Just tell me what is the group of symmetries for them. And from that, in principle, I can deduce what these polynomials are. And so geometric complexity theory So, by the way, this is a nice exercise to do to try to figure out exactly what are the symmetries of the determinant and the permanent. So, and the once you figure out exactly what is the group of symmetries, it's relatively easy to see that these two polynomials are in fact characterized by their symmetry. So, so perhaps the clue to the hardness or easiness of this polynomials lies in the group of symmetries. That is sort of the starting point of geometric complexity, and it goes on to try to understand the representations of these groups, of this group of symmetries, and tries to argue about the complexity depending on what the representations are. So roughly that's a program. So let me tell you about this other approach called the real tau conjecture. So it starts from this fact. Suppose you take a univariate polynomial now over integers and ask how many integer roots does it have. Now it turns out that if you have a degree d polynomial which has lots of integer roots and it is efficiently computable, I will tell you what lots of and efficiently computable are in this setting in a short while, but it implies something striking. It says that then integer factoring can be done efficiently on the average. So, but we believe that integer factoring can't be done efficiently. So you ought to probably believe then that any univariate polynomial with integer coefficients that is efficiently computable has only a few integer roots. So this conjecture is called the tau conjecture. It's originally due to Shub and Smale. So here lots of integer roots means say order d or maybe order square root d, and efficiently computable here would mean say polylog d, having circuit complexity polylog d. So let's believe this conjecture for the moment. Suppose if it was true, then it immediately gives you a lower bound. Why is that? So consider this polynomial, x plus 1, x plus 2, x plus d, just a product of d linear polynomials, all of whom have integer roots, distinct integer roots, right? And if you just apply this here, you see that if this was true, then its circuit complexity must be super polynomial in log d. But we seem to be far from proving these kind of statements where you have to argue about integer roots of a polynomial. It involves number theory, and typically number theoretic statements are much harder to prove than algebraic statements. So what if we relax this tau conjecture? What if, suppose if you ask this question, you have an efficiently computable univariate polynomial, how many real roots can it have instead of integers? Integer roots, real roots. So maybe one could try to make this conjecture that the number of distinct real roots of an efficiently computable polynomial is small. But unfortunately, that turns out to be false, and counter examples are known. But in some sense, all the counter examples that we know of for this statement have high depth circuits. So, so here's what the real tau conjecture says. The number of distinct real roots of a univariate polynomial computed by a low depth circuit is small. I won't quantify low depth and small here, but intuitively this is what it says. So there has been also some progress along this direction, but I particularly like one question which arose in connection with this. So I'm not sure exactly who posed this first. To me it was posed by Arkadev and Pascal Koiral. It asked this very seemingly looking toy kind of problem. It's a really nice problem. So suppose you have a S sparse polynomial, univariate polynomial with real coefficients, which has at most S monomial. There's a classic theorem which says that such a polynomial can have at most S real roots. This is independent of the degree of the polynomial. This depends on the number of monomials. Okay, so now you suppose you have two sparse polynomials. You multiply them, then each of them has at most S roots, S real roots. So F times G can have at most S real roots, 2S real roots. But now, how many roots does F times G plus 1 have? We don't know. We don't know. The best upper bound that we know is S square, and that's simply because F times G plus 1 has S square monomials, and we do know that there exists polynomials F and G where the number of real roots is more than 2S, something like 3S, but we don't know basically what is the right answer here. So the hope for this line here was that maybe it's easier to argue about, maybe one can use tools from real analysis to argue about the real roots of a polynomial. So, any questions so far? So, where the de-randomization of polynomial identity testing. So recall the polynomial identity testing problem. You are given a circuit C. You want to determine whether its output is identically 0 or not. And this is an algorithmic problem. And intuitively, as computer scientists, we are much more used to, or have been much more successful in devising algorithms rather than proving lower bounds. So maybe we can solve this algorithmic problem, and that will give us circuit lower bounds. So let me tell you what is the connection of this problem with circuit lower bounds. And this is also well known. I forget who originally observed this. Sorry? Heinz and Schnorr, yeah. So here's how it goes. So suppose, assume you have the strongest possible kind of identity testing algorithm you could hope for. So, which means the following. So you have a bunch of points, polynomial in S, number of points, with the assurance that for any circuit of size S, if you hit that circuit with one of these points, then at least one of the outputs must be non-zero. So if you had such an explicit set of points like this, you could obviously de-randomize identity testing, just check the output of the circuit on each of these points. Now, why does it lead to lower bounds? You can interpolate an F supported over more than M monomials, which vanishes at each of these points. So pick your favorite set of M monomials and just calculate the coefficients of these monomials such that the polynomial vanishes at each of these points. And you can do this because all of each such f of pi being 0 is imposing a linear constraint, a homogeneous linear constraint on the coefficients, and if you have more coefficients than the number of points, then you can always find a non-trivial solution. So here it should be for any non-zero f of circuit complexity f, f of t is and so we will see more talks about identity testing. Now, the final thing that I want to mention is trying to prove lower bounds by trying to prove lower bounds for small depth circuits. So let's recall this depth reduction result that I mentioned, that if you take any circuit of size s and degree d, you can simulate it by a small depth circuit. Pick your favorite number delta. You can simulate it by a circuit of depth delta, but now the size blows up to s to the d to the 2 by delta. And here let's recall that we are thinking of all the gates in the circuit having unbounded spanning. So for example, if you have to pick delta to be log d, from polynomial size circuits you will get to log depth circuits of polynomial size. If you pick delta to be 4, then from polynomial size circuits you will get to circuits of size n to the root d. So in fact, the circuits that we get this way have some more special structure. They are homogeneous, and you can put a bound on the degrees of the polynomials computed at each node, but let's forget about that. Depth 4 circuits of size n to the root d. So you could try to prove lower bounds against the circuit. So let's say if you have a lower bound, if you have an explicit polynomial which requires depth 4 circuits of size more than that, then that must require super polynomial arithmetic circuits overall. So this is what one tries to do here. There are other similar results. For example, one is by Granras, where he starts with formulas and reduces them to depth 3 circuits of a very special kind, and called tensors, and the hope is that one can prove lower bounds on ranks of tensors and reduce lower bounds for formulas. And recently there was a reduction to depth 3 also with similar kind of parameters. So, okay. Any questions? So let me tell you about depth reduction. And Ram Prasad helped me prepare the slides here and the proof here. So this is the theorem I want to present. There are various variants of it and versions of it in a sequence of papers, but and they are different in some ways, but very roughly, let's say that pick your favorite depth delta, then starting from a circuit of size s, you get a circuit of size s to the d to the 2 over delta. And it turns out that this holds even for Boolean circuits. But in the case of arithmetic circuits, the nice thing is that we can assume essentially without loss of generality, because of what I told you earlier, that the degree of the circuit actually equals the degree of the polynomial that we are trying to compute. Okay. So, I'll just go on to the proof. So here, let's make a first attempt at this. It won't succeed, but it will. We'll just see what's the problem. Okay. So suppose you have a circuit computing a polynomial. In this case, it's H. So one way to try to do depth reduction might be you choose a subset of the nodes which form a cut in the graph corresponding to this circuit, and cut the circuit at this set of nodes, so into two pieces. Take this bottom piece, let's say the nodes at the frontier, they compute some bunch of polynomials h1, h2 through hm. There are m nodes at the frontier. Now they feed into the top half of the circuit, right? So now let's think of the top half of the circuit as taking m inputs, and so the top half of the circuit, it computes some polynomial over these m variables y1 through yn. These are just new variables I have introduced, and ultimately these yi's will, each of them will get replaced by hi, which are polynomials in the original variable. So now suppose we do the following. We take this top half, but we just expand this polynomial h of y as a sum of monomials. So we have expanded h of y here as a sum of monomials, and now we replace this top circuit by this depth 2 circuit. So maybe this can reduce the depth. Okay. So, and now what about the size? The size might have blown up because I have replaced a circuit by its sum of polynomials, sum of monomials representation. But suppose h of y had a few monomials, only a few monomials, then I would not have increased the size also by too much. Okay. So when does this, how can we make sure that h of y has few monomials? One way to try to make this happen is to make sure that h of y has low degree as a polynomial over the y variable. But now there's a problem. So it seems to work, but if you think about it, very quickly you will see a problem. So overall the circuit looks like this. Now the problem is the following, that in our original circuit that we wanted to do surgery on, there might not be a good correspondence between the degree of a node and its distance from the input node. So you can have a node which occurs very close to the output but which might have very small degree, and something or you could have nodes which are in some sense very close to the input layer but which have very high degree. So if there was some sort of correlation between the distance from the output and the degree of a node, then this might have worked, but in general this need not be the case. But one thing that we will use from all this is the following simple notion. So it will, in many of these arguments, it will be helpful for us to do the following. Suppose you have a circuit like this. Pick a pair of nodes. Pick some set of nodes. Say maybe you pick a pair of nodes, U1 and U2. I want to think of my output as a polynomial over the input variables and the nodes U1, U2. So what do I mean by this? Suppose you do the following, you remove all input edges going into U1 or U2. So you sort of discard the sub-circuit underneath U1 and U2 and replace them by formal variables, Y1, Y2. If you have to do that, your output would be a polynomial over the original variables and these new variables, Y1 and Y2. Okay? And we'll be doing this often, and we'll especially be concerned with the degree of H with respect to just these Y1, Y2 variables. That will be also very important for us. So for now, let me give an overview of the proof. I will assume the following lemma. So for this naive thing to work, basically by doing this operation you want the depth to go down and the circuit size not to blow up too much. And if you think about it, so the trade-off that you get here will depend on what is the degree of the top polynomial versus what are the distance of how much reduction in the depth you have gotten. And the reduction in the depth that you get depends on how much depth you have cut off, which depends on what is the distance of these nodes in the frontier. And the increase in size you get depends on the degree of it. So roughly that is. So it doesn't work anyway, so maybe go on. Okay, so suppose our circuit had the following nice property, that every node every multiplication node has at most 5 children, and for any child of a multiplication node, its degree is at most half the degree of the parent. So, it turns out that given a circuit of size S, you can efficiently convert it into a slightly larger circuit where this property holds true. And this is the main lemma in all this. But let's assume for the moment that this is true. Let's see why it will imply a depth reduction. Okay. So this lemma, it implies the following, that take any node V in this new circuit. So for the moment I will assume that our circuit has this low degree children property. For every multiplication node, its children have degree at most half the degree of the parent. Okay? So now take a node of some degree E in this new circuit, C, and pick any integer R. Then you can express the polynomial computed at the node V as a sum of product of polynomials computed at low degree nodes. And this you can always do trivially, but one needs to quantify this. So by low degree nodes, I mean nodes which have degree at most R, and we'll see that the number of summands in this expression is at most S to the E by R. So the number of summands is not too large. So why is this? So here's the overall proof. One first proves the low degree children, that lemma, that a circuit can be converted into another with low degree children. Then you can write a polynomial as a sum of product of low degree nodes, and this will give you the depth reduction theorem. So let me first give the second part of this overall proof. So suppose you assume this is true, and let's say the target depth that we want is 4. So you want overall a depth 4 circuit. So what would you do? So take the circuit, color the nodes into, say, 2 colors, blue and red. Blue is all nodes having degree more than square root d, and our circuit is homogeneous, so degree is at most d. And red is all nodes having degree less than or equal to square root d. So now do the following. For every red node, now let's make a depth 4 circuit. For every red node in the original circuit, put a red node at level 2 of this new depth 4 circuit. There's a 1-1 correspondence here. Just write the polynomial computed at each node here as a sum of products of the input nodes. And when you do this, for this part, choose R to be 1, and this corollary assures you that for each red node, the circuit underneath it is a sum of products circuit, so depth 2 circuit, and it has size S to the square root d. Now, now do the same thing with the blue nodes. For the blue nodes, choose R to be square root d. So now each of these blue nodes have degree at most d. So again, if you apply this lemma, you can write it as a sum of product of the red nodes, and each such sum of product expression has size S to the d by root d, which is S to the root d. And if you put this together, you get overall a circuit of size root d. And you can do this for arbitrary delta, arbitrary target depth. For example, if you wanted a depth 6 circuit, you would divide your the nodes in your circuit into 3 colors, red, say red, blue, green. All nodes of degree between 0 and cube root of d you put into one class, between cube root of d and d to the 2/3 you put in another class, and so on. So this generalizes in a very straightforward way for arbitrary delta here. Yes. Right. No, it does not depend on d phi. Actually, that's we calculated this constant. Well, at most 50. You can probably improve that. Okay. So let's see why having low degree children is useful. So now we want to prove this implication, that the main lemma implies this corollary. So just give you a moment to digest the statement here. So, this is also fairly natural. So, so, so assume our circuit has this low degree children property. So, you start with a node V. You want to write it as a sum of products of polynomials at small degree nodes, and you would like to do the natural thing. So, you start with this node of V, and you could write it as a sum of product of its children or grandchildren. So, if V is a plus node, write it as a sum of product of grandchildren. If V is a times node, just there's one summand only, which is as a product of its children. You could always do this, and this the number of summands here initially is at most s, the number of nodes in the circuit, right? Because in particular, any node has at most s square children, s square grandchildren, general term. Okay, so now, so we have obtained. So, but now our circuit has this nice property that the children are of low degree. So we have obtained some reduction on the degree here. If this was of degree E, all these are of degree at most E by 2. So now you repeat this, but we want to get towards target degree R, which is much. If R was equal to E by 2, then you would be done here already. But if not, you repeat this. So in each term, you do the following. Take the factor. So fix a term here, like a product of polynomial. Take the factor which has the largest degree. So that factor is in fact the output of some node in the circuit. Replace that by again a sum of product of its grandchildren. So in each term, keep on reducing the degree in this natural way. And it turns out you can analyze this, and this analysis was told to me by Ram Prasad, that you can bound how many iterations you require to push the degree down to R, and this the number of iterations required is E by R. So overall, you would have blown up the sum of product representation by s to the number of. In each iteration, you blow it up by a factor of at most s square, and there are these many iterations. So overall, you get s to the order E by R many summands here. So this proves the corollary. Now, I was planning to prepare slides for the main lemma, but I will use the board instead. Easier to describe it because on the blackboard. So let's just recall the main lemma. We have an arbitrary circuit C. We want to get another circuit C prime maybe, where every node has small degree children. So here's what you would suppose. You pick a node V in my circuit. It has some degree E. Now, consider this collection of nodes. Okay. So consider an arbitrary circuit in which we have a node of degree E, and now consider this set of nodes, all of them of degree between say E by 2 and E by 3. And there's some polynomial computed at this node, let's call it Fv. Now let's do the following. Let's look at Fv as a polynomial over the input variables and these nodes in the sense that I described earlier. What this means is I remove the sub-circuits underneath these nodes. I just remove the inputs to all these nodes and replace them by formal variables y1 through yr, and there are the inputs x1 through xn. Feeding into the circuit as before. Now, so think of Fv as a polynomial over y1 through yr and x1 through xn. Now let's look at the degree of Fv as a polynomial in the y variable. So here's the claim that this degree can be at most 2. Why is that? Because if Fv has say a monomial like y1, y2, y3, then so each of y1, y2, y3 has degree at least more than e by 3, and if Fv had a monomial like this, its formal degree would be more than e. So as a polynomial over the y variables, it looks like this. It's quadratic, at most quadratic in dy, and the coefficients are some polynomials over the x variable. Now, so now you do this for every node v. You get a bunch of polynomials over the original variables x1 through xn. So associate this set of polynomials with this node v, and the main idea of Valiant was that instead of trying to argue about each node individually, let's compute all these polynomials Gijs that you get for all the nodes simultaneously. That's, and so here's the idea. Consider union of all Gijs. So let's call them Gijv for all nodes v. Let's call this set of polynomials S. So these are polynomials over the original variable. Let's compute each of them, all of them simultaneously. So now it turns out that you can argue about these polynomials, keep track of their degrees, and so here's what you do. Take this set of polynomials, compute first, at the first step, compute all polynomials in this set of degree, say, 1, between 0 and 1. Then all polynomials of degrees between 2 and 3. Then all polynomials of degree between 4 and 7. and then 8 and 15 and so on. And so if you think about it, it turns out that you can do this computation in a very nice fashion inductively like this, and it will, and if you look at the graph of this computation, it will have the low degree children property. So, so I'll end my proof sketch for variant here. I waived this last bit here, but this last bit, just believe me that it's verifying that if you try to compute all of them simultaneously in this way, then it works. You can connect up all the nodes in the most natural fashion that you want to do that you would have done that, and it has this low degree property. So, any questions? Okay. So let's move on to some circuit lower bounds. I want to present one lower bound by Jerem and Snell. So it's much easier than Rasborov's monotone Boolean circuit lower bound. I like this. I'll give a slightly different presentation of this. So let's see what are monotone circuits. So suppose your underlying field is the field of real numbers. So call a circuit monotone if all the constants that occur in the circuit are positive, or at least non-negative. So, so in particular, you cannot do subtraction, and the function that you compute at the end of it will always be a monotone function. If you increase the value of any variable, the function can only increase, it cannot decrease. But this definition, it makes sense over the real, but not over, say, S3. And such circuits can only compute polynomials with positive coefficients, because you never have negative numbers coming in the picture. Right? So I want to give a slightly different presentation, which will make sense over all fields and for all polynomials. So let me motivate that. So let's do the following. For every node in my circuit, I will associate a set of monomials to it in a very natural way. So, for example, for every input node, no matter what the constant is, if it's a constant, then just associate the monomial 1 with it, unless it's a 0, in which case you set it to 0. For every variable node, xi, the monomial corresponding to it is just x. The set of monomials corresponding to it is just xi. And now you do inductively, just like we defined in the formal degree of a circuit inductively. So if you have a times gate, you multiply the set of monomials corresponding to its children. So this multiplication is element by element. So it's the product of all monomials in this set times everything in this set times everything in that set. That's the set of monomials. And similarly, if you have a plus gate, just take the union of the two sets corresponding to the children. And why am I saying all this? It's because for the usual notion of monotone circuits over real, you make the following observation, that at the output node, the set of the formal monomials that you get must be exactly equal to the set of monomials in the output of the circuit. Because intuitively a monotone circuit cannot have any cancellation, so if you were to produce any other monomial, you could not cancel it off. So it has to be exactly equal. So let's define monotone circuit like this. It's a circuit in which at every node in the circuit, the formal set of monomials at that node is exactly the set of monomials in the polynomial computed at that node. So the theorem is the following. Any monotone circuit computing the determinant must have size at least, must have exponential size. Yeah, but this makes sense even for negative coefficients because, yeah. The whole point I wanted to present it this way was makes sense for any polynomial over any field. Okay, so here's a lemma. The proof of this lemma is very similar to the arguments involved in depth reduction. You intuitively you so suppose you have a circuit of size S computing a polynomial, say the determinant, then you can express it as a sum of products of polynomials. These Fi's and Gi's are essentially polynomials computed at intermediate nodes in the circuit, and you can choose them in the following way, that the degrees of each Fi and Gi is bounded by, is between d by 3 and 2d by 3. And the number of summands that you get this way is at most the size of the circuit. And because these Fi's and Gi's are intermediate nodes in my monotone circuit, it also holds that the set of formal monomials computed at Fi times Gi, this must be a subset of the monomials computed at determinant, subset of the monomials in the determinant. Right? From our because from our definition, basically we want to disallow cancellation. So you cannot generate any extra monomials than are already present in the determinant. Oh yeah, sorry, somewhere yeah. So this D is N actually. Okay, so let's see why. Now, if you just stare at this, the key thing is now these two facts allow you to deduce that the number of monomials in each term, Fi times Gi, must be small. But it's not very small, it's actually exponentially large, but it's not small compared to the determinant. So let's see exactly what that is. So let's stare at an expression like this. So the determinant, I've written it as a sum of products like this, Fi Gi. The degrees of the Fi's and Gi's are between n by 3 and 2n by 3, and the monomials generated at each term is a subset of the monomials occurring in the determinant. So let's make some observations. So for each of these Fi's and Gi's, let me make the following notation, row support. It is, so our determinant is the determinant of a formal matrix with n square variables, n cross n matrix. So now Fi will have some subset of variables, and look at collect together all the row indices in each of the variables that occur in Fi. Call that the row support of Fi. All the rows in the matrix that Fi touches. Right? And similarly for Gi. So you observe the following, that first of all, the row support of Fi must be disjoint from the row support of Gi, right? Because in the determinant, every monomial is from distinct rows. In the determinant, in every monomial, all the variables are from distinct rows. So if there was some row, say 1, from which some variable occurred in both Fi and Gi, then that will violate the property about the monomials of the determinant. Okay, and in fact, these two must complement each other. Again, basically for the same reason. These one more thing, these must also be homogeneous polynomials, and their degrees must add up to n. So the row support of Fi must exactly be the complement of row support of Gi. What we really need is that these are disjoint, but anyway, it turns out they are exactly complements of each other. And by symmetry, the same thing holds for the column supports also. Any questions? And now, so now Fi and Gi each compute monomials. Say Fi computes the row support of Fi is over the first R rows and R columns, and it computes a bunch of monomials. Then all those monomials that you get must correspond to permutations in this submatrix. Again, I'll leave it as an exercise. Again, if it was not a permutation, it would violate this condition, that you will have generated a monomial which does not occur in the determinant. So, okay. So each monomial in Fi corresponds to a permutation over the submatrix that it touches. Similarly for the Gi, and the submatrix that Fi touches must have size between n by 3 and 2n by 3. So in fact, it has the submatrix that Fi touches has size exactly the degree of Fi, which is between n by 3 and 2n by 3, and similarly for Gi. And since the degrees are bounded like this, you can verify that this expression is bounded by n by 3 factorial times 2n by 3 factorial. Intuitively, the worst thing to do here is to make them as unbalanced as possible, the degrees. Okay. So then, if you just look at how many monomials there are in the determinant, there are n factorial monomials. Each term generates at most these many monomials, so the number of commands must be at least the ratio of these two. And if you recognize this ratio, this is just the binomial coefficient n choose n by 3, which is approximately 2 to the entropy of 1/3 times n, which is exponential. So that's the proof of the monotone surface area. Yeah. So any questions? Yeah. Yeah, you can. Yeah. No, basically you apply this way of. So you start at the output and you try to express f as sum of products of these intermediate polynomials. But there's one caveat: these GIs are not exact. I cheated a little bit. These GIs are not exactly intermediate things, but it's one of these coefficient polynomials here in some sense. But basically, sort of apply this to this setting and use that. So the question is, will this same proof work for iterated matrix multiplication or not? So, I mean, if I'm right, there's a theorem which says at least for 2 by 2 matrix, I mean, for n cross n matrix multiplication, for multiplying just 2 matrices, if you have a monotone circuit, then it must be of size at least n cube. So what Amir is saying is that for iterated matrix multiplication, there's a small branching program, and if you just look at the branching program, it's monotone. You never use negative steps.